Welcome to my presentation. My name is Korawich. I am excited to share with you our paper about street-level urban gravity, a quantum system approach to human-centered urban space design. Let me start with this observation in 1980. The lines and dots here represent social connections and location of social activities. You can see that a lot of people tend to socialize here on the street with light car traffic as opposed to the road with heavy car traffic. This is another example of how the built environment influences social interactions. They are both coffee shops, but one seems to have more chance of having social activities than the other. Although this mechanism behind this relation was not rigorously defined with any science, people in the past have been aware of this mechanism for a long time. In 1675, King Charles II knew the potential of coffee shops and attempted to ban all of them to reduce political gossip in England. This is, again, another example. It's a garden of the office building in New York City. So there is something about the way we design or engineer urban space that can potentially influence human behavior in that space, as if there is some energy there that can create some kind of gravitation. Of course, I am not the first one who thinks about this physics analogy. A lot of studies, especially in transportation, have come up with many models ranging from macroscopic to microscopic level. Some of these models directly follow Newtonian gravity models, some of which are now standardized for predicting trip distribution. Some models work with micro and mesoscopic, and they make analogy to fluid mechanics, which instead of mass flow, it is car flow with some cost function in its street. After exploring literatures in many fields, I noticed that there are three problems that many theories have not simultaneously addressed together. Firstly, transportation people seem to have a mindset of thinking about it as an A to B process. Now that's okay for driving, yes. But when you walk, your experience along the way at each point here and there becomes more critical when you think about walkability. Secondly, I am more interested in pedestrian position and their behavior. A street is sometimes a place where you want to go to, not just go through. So it's not just about flow. Thirdly, I want a model to provide me with an insight of urban space, not just a model that I can feed the data in and give out value or something. This is just to show some of the works that done with uh, analogy to physics. The first one is analogous to fluid mechanics. Second one used electric charge, and the third one is like a tidal wave. One more thing to note is that while it did account for more than just flow values, the idea is still very deterministic. The idea in this paper is that there is some kind of system that the physical urban space acts to the behavior or state of human in that space. This state of human can be thought as a mathematical description of their position and momentum. In this microscopic world, these human emoji are what I like to refer as urban particle. The energy that you have simply by existing at that position is what I call urban potential. You can think of it as a gravitational potential field. And by solving this funny looking differential equation, which is Schrödinger equation, we get this psi, which is a wave function of urban particle. This is a ket notation, which have information that can be represented with either position or momentum. We will come back to discuss why quantum particle later on. The question becomes, how do we get this potential V? It is obviously not E equal mgh. The approach here is to incorporate the idea of multisensory architecture. Basically, you can think of an urban particle that has these 5 senses attached to it, and its reading of sense change based on the design. The first 3 senses here, eye, ear, skin, have been explored well. They just don't call it urban potential. But the last 2, especially this last one, they are challenging, unless you want people to lick concrete wall and access to your values. But I think this is a very interesting idea because it also explains why would someone would experience something differently given their conditions. For example, if you think about a blind person, their experience on urban space could be different from the person who have normal visions. Now let me clarify this wave function and its interpretation. The wave function itself has complex value and it is a vector in Hilbert space, but its norm square is real and has real meaning, which is the probability or probability density. Imagine a camera on a plaza like this. If we take a video and overlay multiple snapshots from the video, you have this picture. The spot that has a lot of black pixels is the spot that you will likely to find an urban particle, which is exactly how the electron in an atom model is modeled. This is what quantum physics provides us that classical physics cannot. It provides a door, something new to probabilistic, something that's more than just deterministic. You might be still asking, why not just go with classical math? Why wave function? And I think it comes down to which way of model reflects how human behave the most. If we think about like a double slit experiment, but we model our urban particle as a mass ball, then from this people shooter, it must go into the slit directly as a straight line. There should be no interference with one slit and another. But we humans are much more chaotic than that, more than classical math. We can also think about it with the Feynman path integral, which is a model that predicts a walking path as a sum of all possible actions, which if you think about it in terms of energy, you eventually come back into Schrödinger equations eventually. Of course, we can come up with any theory. The real fun part of it is to do some sort of test-based experiment, which is where I am right now. I am using the data of a neighborhood in Pittsburgh, Pennsylvania, ranging from building models, census data, weather conditions, and map this out in my toy model in Rhino 3D. This is a setup for the potential, which by assuming some starting source of urban particle, we can numerically solve Schrödinger equation in Python and get this wave function square. Future work on this toy model is still ongoing. But you might be still asking, what's the point of all this? One reason I believe quantum physics is fascinating is that quantum particles sometimes violate the law of classical physics. In transportation engineering, we think about jaywalking as a bad behavior that can be neglected in most projects. But if you look into jaywalking, you will find that it is a term coined by a car company in 1920 to shift the blame to people that get hit by a car, because back then the street was never built for cars. In many urban areas, highways act as a barrier separating local communities. But the need to walk is still there. It's our nature. Quantum mechanics did exactly this. It is possible for particle to tunnel through the potential barrier, even though it does not have enough energy. And this can later be applied to any future traffic signal design or business analysis on the other side. It's like the famous quote from two scientists. One said, God does not play dice. Another one replied, don't tell God what to do. I would like to acknowledge all the help I got to make this paper possible, and thank you for your attention.